Hey friend, tonight we're heading to the far edges of theoretical physics, into the realm of white holes. They're the mysterious time-reversed twins of black holes, predicted by Einstein's equations but never observed. Yeah, so get cozy, let your mind drift, and let's explore the universe together, one impossible idea at a time. Chapter 1. What are white holes? The mirror image of darkness. In the great tapestry of the universe, few concepts provoke more curiosity and confusion than the idea of a white hole. While black holes have become almost household names, featured in everything from science fiction to Nobel Prize-winning research, white holes remain largely obscure despite being their theoretical twin. Emerging naturally from the same equations that predict black holes, white holes are strange and paradoxical objects, regions of space-time that cannot be entered from the outside, but from which matter and light can escape. If a black hole represents a point of no return, a white hole is, in some sense, a place of no approach. To understand what a white hole is, it helps to first understand the framework in which such an object arises. Einstein's general theory of relativity, formulated in 1915, describes gravity not as a force, but as a geometric curvature of space-time. Massive objects like stars and planets warp the fabric of space and time around them, causing what we perceive as gravitational attraction. Under extreme conditions, this curvature becomes so intense that it produces a singularity, a point where density becomes infinite, and the known laws of physics cease to apply. Black holes arise from this process. When a sufficiently massive star exhausts its nuclear fuel, it can collapse under its own gravity, shrinking inwards without limit. If nothing halts this collapse, not even neutron degeneracy pressure, the star continues compressing until it forms a singularity. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape, not even light. Once inside, all paths lead inevitably inward. Time and space seem to switch roles, and the arrow of time points toward the singularity. The equations that describe black holes, particularly the Schwarzschild solution to Einstein's field equations, are time-symmetric. This means that if the equations allow a black hole to form by matter collapsing inward, they must also allow for the time-reversed version of that process, a white hole, which expels matter outward but cannot be entered. In this sense, white holes are not ad hoc theoretical inventions, but rather mathematical counterparts to black holes. They arise as part of the full, extended solution to the Einstein equations, describing a non-rotating, uncharged black hole. The story of white holes is as much a mathematical curiosity as it is a historical reflection of how theoretical physics evolves. Shortly after Carl Schwarzschild published his exact solution to Einstein's field equations in 1916, it became clear that the solution included peculiar features. One of these was a singularity, a point where the curvature of space-time became infinite. Another was the event horizon, a spherical boundary beyond which the metric appears to become undefined. These early results were poorly understood for decades, and even Einstein himself was skeptical of physical singularities. For a long time, black holes were seen more as mathematical oddities than real objects in the cosmos. It wasn't until the mid-20th century that physicists began to explore the full implications of the Schwarzschild solution. In 1958, the physicist David Finkelstein provided a clearer physical interpretation of the event horizon, showing that it was not a true singularity, but a causal boundary. A few years later, in 1960, Martin Kruskal and George Sekaris independently developed a new coordinate system that allowed for the maximal extension of the Schwarzschild metric. What they found was surprising. The extended solution described not just one black hole region, but 4 distinct spacetime regions. These included a region outside the black hole, where we exist, the black hole's interior, a parallel universe beyond the event horizon, and crucially, a white hole region, a mirror image of the black hole, where matter emerges but cannot enter. In the Penrose diagram representing this geometry, the white hole occupies a symmetrical position to the black hole, reversed in time. Its existence was not something added to the equations, but something that naturally fell out of the mathematics. But what does it mean for something to be the time reversal of a black hole? In simple terms, imagine playing a video of a black hole's formation in reverse. Instead of matter collapsing inward and disappearing behind an event horizon, you would see matter spontaneously ejecting from a singularity, with an event horizon that nothing can cross from the outside. While this may sound fantastical, it is exactly what general relativity predicts in its most complete analytical extension of the Schwarzschild geometry. In this extended geometry, which includes both black holes and white holes, the spacetime diagram shows not just one region, but several interconnected regions. One of them corresponds to the familiar external universe, where observers like us live. Another is the interior of a black hole beyond the event horizon. A third is the white hole region, where the time-reversed behavior takes place. And finally, there is a second external region, possibly representing a separate universe. This complex structure suggests that, at least in theory, black holes and white holes might be connected through a kind of wormhole or bridge, a concept we'll explore more deeply in later chapters. Despite their firm footing in the mathematical structure of general relativity, white holes raise immediate and profound physical challenges. First and foremost is the question of their stability. While a black hole pulls matter inward, the white hole repels it. But this repulsion creates an instability. Any slight perturbation in the surrounding space could lead to the immediate collapse of the white hole structure. Theoretical models show that even tiny amounts of external matter could cause the white hole's event horizon to disappear or invert, effectively turning it into a black hole. This leads many physicists to view white holes as mathematical curiosities rather than real astrophysical objects. Another complication is entropy. In the observable universe, processes tend to increase entropy, a measure of disorder. Black holes famously obey thermodynamic laws, including the increase of entropy. White holes, by contrast, would appear to violate this principle. They would seem to decrease entropy by emitting organized matter and energy into the universe, something that does not match our experience of time and thermodynamics. This tension between the mathematical possibility of white holes and their physical implausibility is one of the key reasons they remain unobserved and largely speculative. Still, their theoretical presence raises interesting questions. If nature allows for time reversal symmetry in its most fundamental laws, then why don't we see white holes? Could they exist in some other form or during the early stages of the universe? Are there mechanisms that might prevent them from forming or hide them from our view? Or are they simply relics of an idealized model with no correspondence in the physical world? Interestingly, white holes have appeared in a number of speculative cosmological theories. Some researchers have proposed that the universe itself may have emerged from a white hole-like event. Others suggest that information falling into a black hole could be ejected from a white hole in a different region of space-time. While these ideas remain highly theoretical and lack direct observational support, they underscore the role of white holes as conceptual tools for probing the deepest mysteries of time, gravity, and the fabric of reality. It's important to emphasize that no white hole has ever been observed. Unlike black holes, which can be detected by their gravitational effects on nearby matter and light, white holes would be nearly impossible to approach, let alone study. If they do exist, they might manifest as sudden, high-energy bursts of matter and radiation with no discernible source. An idea that has led some to speculate about possible connections with phenomena like gamma-ray bursts or fast radio bursts. But these associations remain speculative, and no definitive evidence has yet been found. In the modern scientific landscape, white holes occupy a strange position. They are not dismissed outright because they are rooted in legitimate mathematics. Yet they are not embraced as real objects either, because they seem to defy the physical and thermodynamic laws that govern our universe. Their presence in the equations of general relativity is a reminder that not all mathematical solutions correspond to physical reality. But they also remind us that reality might be deeper and stranger than we currently imagine. The story of white holes is, in many ways, a story about the boundaries of our understanding. It illustrates the tension between mathematical beauty and physical truth, between what equations allow and what nature permits. In the silent elegance of Einstein's equations, white holes are as valid as black holes. But in the noisy, chaotic universe we observe, they remain elusive, perhaps hidden, perhaps impossible, or perhaps waiting to be discovered in ways we have not yet conceived. And yet, the idea lingers. Something about the symmetry is too elegant to ignore. If there are places in the universe from which nothing escapes, could there also be places where everything escapes, never to return? Could there be cosmic fountains spewing the contents of other worlds, unreachable and unknowable? It is a question that lives at the intersection of physics and imagination, where equations brush up against the limits of human intuition. In the quiet hours of the night, when the universe stretches out infinitely in all directions and time feels like a slow-moving current, it's hard not to wonder, if black holes are the universe's secret keepers, could white holes be its storytellers, forever releasing echoes from a past we'll never know? Chapter 2. Inside the black hole, the birthplace of the white hole idea. Black holes are among the most extraordinary predictions of general relativity. They challenge not only our understanding of physics, but also our intuition about how space, time, and causality function. While black holes have gradually moved from theoretical abstractions to observational realities, white holes remain suspended in a realm shaped almost entirely by mathematics. To understand how white holes enter the picture, we must examine the precise geometry of black holes, particularly the Schwarzschild solution, and explore how the internal structure of these gravitational wells leads, almost inevitably, to their time-reversed counterparts. The Schwarzschild solution, published in 1916 by Karl Schwarzschild, just months after Einstein presented the field equations of general relativity, was the first exact solution to those equations. It described the space-time geometry outside a spherically symmetric, non-rotating mass. At first glance, the Schwarzschild metric appeared to contain two singularities, one at the center, where the radial coordinate becomes 0, and another at a certain radius, now known as the Schwarzschild radius. Early interpretations treated both of these as physical singularities, points where the laws of physics broke down. Over time, physicists began to understand that not all singularities were created equal. The central singularity at 0 radius is indeed considered a genuine physical singularity, where space-time curvature becomes infinite. The Schwarzschild radius, however, turned out to be something subtler, a coordinate singularity, not a physical one. Just as a globe appears to have a singularity at the poles when described in certain coordinate systems, the Schwarzschild radius emerged as a place where the chosen coordinates failed, not the underlying geometry. It was not until the 1950s and 60s that physicists developed more appropriate coordinate systems to explore the full implications of the Schwarzschild geometry. The most influential of these was introduced by Martin Kruskal and George Sekaras. Their new coordinates extended the Schwarzschild solution beyond the event horizon, allowing for a complete view of the space-time structure. What they discovered was deeply surprising. Rather than a one-sided gravitational trap, the Schwarzschild solution, when fully extended, describes a much richer spacetime, one that includes not only a black hole, but also a mirror image, a white hole. This full geometry contains 4 distinct regions. There is the external region we are familiar with, where an observer could orbit a black hole. Then there is the interior black hole region, bounded by an event horizon, where space-time funnels inward toward a singularity. But Kruskal and Shekaris also revealed the presence of a separate region, a white hole region, also bounded by an event horizon, but one from which matter and radiation can emerge while nothing can enter. Finally, there is a second external region, separate from our own, that is connected through the interior. This structure is not an invention added for symmetry's sake. It is the natural result of solving Einstein's equations fully and consistently. The white hole is not introduced artificially. It arises from the mathematical requirement to extend the solution to its logical conclusion. In the Kruskal-Shekaris diagram, the white hole region appears as the time-reversed image of the black hole. If the black hole is a future-directed singularity, the white hole is a past-directed one. This duality stems from the time-reversal symmetry inherent in general relativity. The equations that describe the gravitational field do not distinguish between forward and backward directions in time. Just as a collapsing star can form a black hole, the equations allow for a star-like object that ejects matter outward, never having collapsed in the first place. This is the white hole, defined not by a physical process of formation, but by the symmetry of the theory itself. Yet the presence of white holes in these diagrams created immediate controversy. Unlike black holes, which could be formed through stellar collapse and later detected by their influence on nearby matter, white holes seemed detached from physical reality. They had no known formation mechanism. They appeared eternal and unchanging, existing for all time in the past and future. While the black hole could be the result of known astrophysical processes, the white hole remained disconnected from observational science. Still, some theorists found this symmetry compelling. If the equations of gravity are truly time-symmetric, then it seemed odd to accept only one half of the solution as real. Why should nature allow for gravitational collapse but not its inverse? If nothing in the equations forbids white holes, perhaps their absence from our observations is due to other factors: thermodynamic, quantum mechanical, or cosmological. Or perhaps they did exist, briefly, in the early universe, before fading into obscurity. To explore these possibilities, we need to look more closely at the behavior of space-time inside a black hole. Contrary to many popular depictions, falling into a black hole is not an instant death sentence, at least not from the perspective of the falling observer. Once past the event horizon, space and time undergo a fundamental transformation. The radial coordinate, which measures distance from the black hole's center, effectively becomes a time coordinate. That is, an object cannot avoid moving toward the singularity any more than it can avoid moving into the future. Inside the event horizon, all paths lead inexorably inward. This behavior is mirrored, in a time-reverse sense, inside the white hole. There, the radial coordinate is reversed. Instead of being drawn in toward a central singularity, particles are compelled outward. They cannot hover near the horizon, nor can they fall inward. The white hole ejects matter as if rewinding the collapse that formed a black hole, but without any initial collapse to speak of. This is a profound inversion of our normal understanding of causality. In a white hole, there is no causal past within the horizon, only a future that spills matter outward into the universe. This odd feature highlights one of the most pressing questions about white holes. How could one ever form? For a black hole, the process is clear. It results from gravitational collapse, as seen in stellar death or the merging of massive bodies. But for a white hole, there is no obvious process that would generate such an object. If it cannot form from collapse, then does it exist only as an eternal feature of space-time? Could it be a remnant from the earliest moments of the cosmos? Or might it arise from quantum gravity effects that we do not yet understand? Some theoretical models suggest that white holes could be the final stage of black hole evaporation. Over time, as black holes radiate energy through Hawking radiation and lose mass, they may eventually shrink to a size where quantum gravity becomes important. In certain loop quantum gravity models, the singularity may be replaced by a bounce, a transition from collapse to expansion, from black hole to white hole. In this scenario, the black hole does not simply evaporate into nothingness, but transforms into a white hole that releases the information and energy it once consumed. Such ideas remain speculative, but they demonstrate the growing interest in white holes as more than just mathematical artifacts. Their connection to black hole interiors, to quantum gravity, and to the fundamental nature of time makes them an irresistible subject of inquiry. The strange geometry revealed by Kruskal and Szekeres opened the door to a space-time that is not merely collapsing, but dynamic and interconnected, a place where beginnings and endings may be linked in ways we do not understand. In this extended space-time, the black hole and white hole regions are linked, not physically in the sense of travel or communication, but geometrically. They form parts of a complete manifold, a continuous fabric shaped by gravity's deepest laws. Whether nature chooses to realize this structure remains uncertain, but the fact that it arises so naturally from Einstein's equations speaks to the power of theoretical physics to illuminate realms far beyond direct experience. Even if white holes are never observed, their role in the development of black hole theory is indispensable. They represent the full implications of space-time curvature and causality. They challenge our assumptions about beginnings and endings, and they remind us that the universe we observe may be only a small part of what is possible within the framework of known physics. In the end, the emergence of white holes from black hole geometry is more than a mathematical oddity. It is a reflection of a universe that may be more symmetric, more interconnected, and more mysterious than we dare imagine. And while we look to the stars for signs of collapse and darkness, we may one day realize that there are also cosmic fountains, places not of silence and absorption, but of radiant emergence. In such a universe, even the most final of endings might not be endings at all, but transitions. The interior of a black hole, long thought to be the ultimate gravitational prison, may instead be the birthplace of something new, a white hole, casting outward the contents of a forgotten collapse. Chapter 3. Time Reversal Symmetry and the Arrow of Entropy. In the elegant equations of physics, time often plays a surprisingly impartial role. The laws that govern fundamental particles, gravitational fields, and even the structure of space-time itself rarely distinguish between the past and the future. Whether a process unfolds forward or in reverse, the equations describing it remain valid. This is known as time reversal symmetry, and it lies at the heart of many of the most fundamental theories in physics. Yet in the real world, time moves unmistakably forward. Cups shatter, but never reassemble. Stars burn through their fuel, but never spontaneously reignite. People grow older, never younger. This contrast between mathematical time symmetry and physical time direction is not just philosophical. It presents a serious problem when considering white holes. White holes, as predicted by general relativity, emerge from the very same equations that produce black holes. They are, in essence, the time-reversed counterparts of black holes. If a black hole represents a region into which matter collapses irreversibly, a white hole is a region from which matter emerges spontaneously, unbidden and unexplained by any known prior state. From a mathematical perspective, the solution is perfectly valid, but from a thermodynamic standpoint, it appears almost nonsensical. The origin of this contradiction lies in entropy. In thermodynamics, entropy is a measure of disorder, or more precisely, the number of microscopic configurations that correspond to a given macroscopic state. The second law of thermodynamics states that in any closed system, entropy tends to increase over time. This law is not a fundamental symmetry like those found in general relativity or quantum mechanics. It is statistical in nature. It arises from the overwhelming likelihood that systems move from ordered states to disordered ones, simply because disordered configurations are far more numerous. This statistical tendency gives rise to what we perceive as the arrow of time. While the microscopic laws of motion allow particles to move backward or forward in time, the macroscopic world overwhelmingly evolves toward greater entropy. A hot cup of coffee cools to room temperature, not because it cannot, in principle, get hotter, but because the number of microscopic states corresponding to a cooler cup is vastly larger than those matching a hot one. The universe as a whole appears to be obeying this rule as well. From the low entropy conditions of the early universe to the complex, thermally equilibrated systems we see today, entropy has been steadily increasing. This presents a profound problem for white holes. For such an object to emit matter in a structured, energetic form into its surrounding environment, it must essentially export a highly ordered state. Imagine, for instance, a white hole suddenly spewing out radiation, particles, and perhaps even coherent structures like atoms or molecules. Where did that order come from? If the white hole had no internal structure or causal history to explain this release, it would violate the principle that entropy must increase. It would seem to lower the entropy of the surrounding universe, which is at odds with everything we observe. In contrast, black holes increase entropy. When matter falls into a black hole, its individual properties are lost to the outside world. All that remains are a few parameters: mass, charge, and spin. This process effectively hides information from the external universe, increasing its overall entropy. Black holes even have an associated entropy proportional to the area of their event horizon, as discovered by Jacob Bekenstein and later formalized by Stephen Hawking. This insight helped bridge general relativity and thermodynamics, revealing that black holes behave like thermodynamic objects. They have entropy, they radiate energy, they slowly evaporate. White holes, on the other hand, do not fit cleanly into this framework. Since they eject matter rather than absorb it, they must begin with a highly ordered internal state to release a disordered spray of energy and particles. But without a causal past, without a process of collapse or infall, there is no known mechanism to establish that initial order. It is as if the universe were rewinding itself locally, in direct contradiction to the global trend of entropy increase. This is not merely an abstract concern. In practice, this thermodynamic inconsistency would make white holes violently unstable. Any interaction with their surrounding environment, even at a microscopic level, would tend to disturb their perfectly ordered boundary conditions. This disturbance would likely cause the white hole to collapse immediately into a black hole. Numerical simulations of white hole solutions suggest that even the smallest perturbation, such as a single stray photon, can destroy the white hole structure. In effect, the universe does not tolerate local reversals of entropy. It selects against white holes not through the equations themselves, but through the overwhelming statistical tendency toward disorder. One might ask whether this argument assumes too much. After all, time reversal symmetry is a fundamental part of general relativity, and one could imagine a universe that runs in reverse, where white holes are common and black holes are the exotic exceptions. But such a universe would look very different from our own. It would begin in a high entropy state and evolve toward greater order, an arrangement that is not only unfamiliar, but thermodynamically unstable. Our universe, as observed, clearly began in a state of low entropy. The cosmic microwave background, the relic radiation from the early universe is remarkably uniform and cold, suggesting a simple, highly ordered beginning. Over billions of years, matter clumped into stars, galaxies, and planets, increasing entropy all the while. This asymmetry between the past and the future, between the low entropy beginning and the high entropy present, is the source of time's arrow. And because white holes imply a decrease in entropy, they run against this arrow. They are not just hypothetical objects that defy observation. They are theoretical structures that seem to rebel against the very flow of time in our universe. There are rare and speculative models in which white holes might be permissible without violating thermodynamics outright. Some physicists have explored the possibility that white holes could be extremely short-lived phenomena, forming from quantum processes and decaying almost instantly. Others suggest that white holes could exist in isolated or disconnected regions of space-time, perhaps in alternate universes or deep within black holes themselves, where the usual rules of thermodynamics do not apply in the same way. But these ideas are far from established, and they do little to reconcile white holes with the macroscopic arrow of time that governs our observable universe. Quantum physics adds an extra layer of complexity to the issue. At the microscopic level, most quantum processes are also time-symmetric. Yet when quantum systems interact with their environment, a process known as decoherence, they exhibit irreversibility, effectively choosing a direction in time. This quantum to classical transition mirrors the way entropy increases in thermodynamics, and it reinforces the idea that the universe has a preferred temporal direction, at least at large scales. Even if a white hole could be supported at the level of fundamental quantum fields, it is difficult to imagine how it could be reconciled with the thermodynamic behavior of the cosmos as a whole. In the broader context of cosmology, this leads to an intriguing asymmetry. The universe permits black holes not only because they are mathematically valid, but because they are consistent with thermodynamics. Their formation increases entropy. Their radiation contributes to the thermal budget of the universe. Their evaporation may eventually return information in a deeply scrambled form, preserving the second law in all its complexity. White holes, however, appear to offer no such compliance. They burst forth, unprovoked, releasing energy and information without any history to justify them. In a universe governed by entropy, they are anomalies, glitches in a fabric otherwise sewn tightly by the laws of probability. The implications of this are not merely technical. They hint at something profound about the nature of time and causality. If the fundamental equations of the universe are time-symmetric, but the universe itself is not, then where does the asymmetry come from? Why does entropy increase, and why did it start so low? These questions remain unresolved, and they lie at the heart of modern physics and cosmology. White holes, as theoretical possibilities, force us to confront these questions head-on. They represent the road not taken, the universe running in reverse, and their absence reminds us that the arrow of time is not an illusion. It is the thread by which our reality is stitched together. And so, while white holes are mathematically impeccable, they remain physically improbable. They are allowed by the equations, but excluded by the laws of thermodynamics and the flow of entropy. They may exist in the pages of theory, but the universe seems to have chosen a different path, one where time moves forward, not backward, and where disorder grows, not diminishes. Still, the idea lingers. Perhaps in some distant corner of the cosmos, in a region disconnected from our own, a white hole exists in defiance of entropy, ejecting the remnants of a forgotten collapse. Or perhaps time as we know it is only a projection, a reflection of boundary conditions we do not yet understand. In that case, white holes might be not just improbable, but inevitable. For now, they remain one of the most beautiful contradictions in theoretical physics, perfect in the equations, forbidden by the world. Chapter 4. The Physics of Ejection. What happens around a white hole? White holes exist so far only in the pristine realm of mathematics. Within the structure of general relativity, they emerge not as arbitrary inventions, but as natural complements to black holes, their time-reversed counterparts. While black holes pull everything inward across their event horizon, white holes push everything outward. If the gravitational collapse of a massive star forms a black hole, then, in a universe governed by time-reversal symmetry, the mathematical possibility of a white hole seems unavoidable. But to move beyond the realm of equations and imagine what a white hole might physically do, what it might look like, how it might behave, and whether it could survive even a moment in our universe, requires a careful dive into speculative but informed physics. At the core of a white hole's predicted behavior lies its most striking property: ejection. Unlike a black hole, whose event horizon marks a point of no return, a white hole's event horizon is a one-way barrier in the opposite direction. Nothing can enter a white hole from the outside, but energy, matter, and possibly information can pour out. This process is not a gradual emission like that of a radioactive decay or Hawking radiation from black holes. It is more like a sudden eruption, an explosive outflow from a boundary beyond which no observer can pass. The notion of matter emerging from a white hole without a known origin poses not just philosophical challenges, but physical ones. Where does this matter come from? If it is emerging from a singularity, then the singularity must be in the past of the white hole's internal geometry, something that exists before the explosion, but which has no causal contact with the outside universe. In classical general relativity, the singularity is not a place in space, but a boundary in time, where known physics breaks down. The emergence of matter from this point into the external universe seems to violate every rule of causality we are familiar with. If such an object were to exist, its ejected material would not simply drift gently into the surrounding cosmos. The gravitational field around a white hole would be just as extreme as that of a black hole, but in reverse. Instead of drawing in objects from nearby space, the white hole's gravity would act as a repulsive barrier near the event horizon, creating a region of high space-time curvature where all trajectories of particles and radiation are directed outward. This repulsion, however, should not be confused with antigravity. It's not that objects would be pushed away by a force. Rather, the geometry of space-time itself would force all possible paths to lead outward. Nothing could linger near the event horizon. Any particle, photon, or observer would be flung away on an unstoppable outward trajectory. The expected emissions from a white hole, should one form or exist momentarily, are speculative, but we can draw some parallels from what we know about energetic astrophysical events. The release might resemble a gamma-ray burst, with an intense flash of high-energy radiation followed by a cascade of particles and shock waves expanding into surrounding space. If the white hole were small, it might emit only a brief flash, a transient burst that would be difficult to distinguish from other short-lived astronomical events. A larger white hole could produce a more prolonged emission, potentially disturbing the structure of its environment and initiating chaotic dynamics in any surrounding matter. The nature of this ejection raises the question of stability. Could a white hole persist, or would it immediately destroy itself through interaction with its environment? Unfortunately for the longevity of white holes, theoretical analysis suggests that their stability is extraordinarily fragile. The boundary conditions required for a white hole to exist are extraordinarily specific. Unlike black holes, which can form naturally from gravitational collapse and maintain their horizons despite ongoing interactions, white holes require a kind of perfect isolation to preserve their geometry. Any interaction with external matter, no matter how small, is predicted to destabilize the white hole solution. The reason lies in the unidirectional nature of the white hole horizon. From the perspective of general relativity, the presence of infalling matter, something attempting to cross into the white hole from the outside, is incompatible with the white hole's boundary structure. The mathematical solution breaks down when this occurs. In practice, this breakdown is expected to manifest as a catastrophic instability. The white hole collapses into a black hole the moment it is touched by the outside world. In a universe filled with radiation, dust, plasma, and quantum fluctuations, achieving this kind of isolation is virtually impossible. Even in the vacuum of intergalactic space, quantum fields fluctuate, particles appear and disappear, and the passage of light carries energy. Any of these perturbations could destroy the delicate white hole configuration. Numerical simulations and perturbative analyses confirm this. The slightest deviation from perfect symmetry, the smallest intrusion from external fields, causes the space-time to evolve toward collapse. In a way, this instability is not surprising. White holes represent an inversion of the natural thermodynamic flow of the universe. Their emissions reduce entropy locally and eject structured information into the environment. This contradicts the statistical tendency of systems to move toward disorder. The instability of white holes may be nature's way of enforcing the arrow of time, not through fundamental laws, but through the practical unlikelihood of such conditions being maintained in a dynamic, entropic universe. If we imagine a white hole existing briefly in some idealized region of spacetime, we can ask what it might look like to an external observer. Unlike a black hole, which can persist as a dark silhouette against a background of infalling material, a white hole would appear as a luminous object of undefined origin. It might resemble a bright sphere, radiating light and matter outward in all directions. There would be no accretion disk, no inward flow of material, and no tidal heating from falling objects. Instead, we might see an expanding shell of ejecta, moving at relativistic speeds, sweeping up interstellar gas and dust in its path. The gravitational influence of a white hole would still be profound. Despite its ejection of matter, the mass-energy content of the object would curve spacetime in its vicinity. Nearby objects could be deflected or accelerated by this curvature, though not pulled inward. The gravitational lensing of background light might be visible, forming distortions or arcs, though these would be difficult to differentiate from other massive compact objects. And unlike black holes which attract and trap light, white holes would repel photons, scattering them outward into space. The tidal effects near a white hole would be intense. As with black holes, the gradient of the gravitational field, how it changes over space, would stretch and compress matter near the event horizon. These effects could lead to the spaghettification of any material that drifted close, even as that material is being expelled rather than absorbed. But again, the extreme instability of the white hole makes it unlikely that anything would get that close in the first place. The interaction would likely trigger the collapse of the white hole structure before significant tidal interactions could even occur. In this way, the white hole presents a kind of physical paradox. Its defining behaviors, its ejection, its repulsion, its horizon are all products of its geometry. But the geometry is too delicate to survive the real universe. The physics of ejection, while theoretically coherent, cannot be realized without a perfectly insulated, idealized environment. Such an environment may exist in the equations, but not in the sky. This raises another intriguing possibility. Could white holes be ephemeral? Could they exist for only a brief moment, flashing into existence through quantum processes, releasing a burst of radiation, and then collapsing into black holes or dispersing altogether? Some speculative models suggest that white holes could be the final stages of black hole evolution. Brief, energetic reversals of collapse near the Planck scale, mediated by quantum gravitational effects. In these scenarios, The ejection is not eternal but momentary, a final outburst of trapped information before the system returns to thermal equilibrium. This concept resonates with ideas from loop quantum gravity, in which space-time is quantized and singularities are avoided. In those models, the singularity inside a black hole is replaced by a quantum bounce, leading to a re-expansion of the trapped material, a kind of rebirth as a white hole. But even in these models, the ejection is not serene or stable. It is violent, chaotic, and brief, more a final gasp than a sustained eruption. And so, when we consider the physics of ejection from a white hole, we are left with a portrait of something fundamentally at odds with the character of our universe. It is an object that can only exist in isolation, that cannot be touched or even grazed without destroying itself. It ejects without origin, illuminates without cause, and vanishes without a trace. It is not simply a rare astrophysical event, but a deep expression of symmetry in a world that does not favor symmetry. Still, the vision is compelling. One imagines a lonely region of space, undisturbed and silent, suddenly lit by a burst of light and matter. No warning, no predecessor, only an eruption from the edge of time, a message without a sender. And then just as suddenly it is gone. In a universe where everything collapses, falls inward, and breaks apart, the white hole stands as a momentary refusal, a fountain flowing against the current of time. Perhaps we will never see one. Perhaps their impossibility is the very reason they matter. Because they remind us that for every rule the universe follows, there exists in principle its inverse. And in the silence between what is and what could be, the mind finds a kind of freedom, a glimpse into what the cosmos might have been if only it had chosen to flow the other way. Chapter 5. White holes in disguise? Could we be seeing them already? White holes remain, for the most part, in the realm of pure theory. Unlike their black hole counterparts, they have not been directly observed, and their predicted behavior conflicts with our most established understanding of thermodynamics and causal structure. Yet there is a persistent thread in the scientific conversation that asks whether white holes might not be entirely absent from the universe, but simply misunderstood. Could they be hidden in plain sight, masquerading as other high-energy, short-lived phenomena that we already observe? Could the cosmos already be whispering the presence of white holes through signals we just haven't interpreted correctly? This possibility, while speculative, is not without some motivation. The universe presents us with a wide range of powerful transient events, explosions and flares that release enormous amounts of energy in very short periods of time. Among these are gamma-ray bursts, GRBs, fast radio bursts, FRBs, and ultra-high-energy cosmic rays. These phenomena are often observed without a clear understanding of their origin. Some appear from regions of space that show no prior signs of activity. Others are one-time events, flaring into our instruments and then fading forever. It is within this landscape of mystery that the hypothesis arises. Perhaps some of these bursts are white holes revealing themselves momentarily before collapsing or vanishing. Take gamma-ray bursts, for instance. These are among the most energetic events known to science. Lasting anywhere from a fraction of a second to several minutes, they release more energy in that brief time than our sun will emit over its entire lifetime. GRBs are typically classified into two types: short-duration bursts and long-duration bursts. The longer ones are generally associated with the deaths of massive stars, the collapse of their cores into black holes, accompanied by jets of relativistic particles. The shorter ones are thought to originate from the merger of compact objects like neutron stars. Yet, despite this classification, some GRBs remain unexplained. They occur far from any visible galaxy, or with characteristics that do not neatly fit into either model. A few researchers have proposed that these anomalous GRBs might be evidence of white holes. Their sudden appearance, immense energy, and lack of a clear progenitor make them plausible candidates, at least on paper. Fast radio bursts present a similarly intriguing case. First detected in 2007, FRBs are bright, millisecond-long pulses of radio waves originating from outside our galaxy. Their exact origin remains unknown. Some repeat, others do not. Some are associated with persistent radio sources, others come from apparent voids. The mystery surrounding FRBs has given rise to a wide array of hypotheses, from magnetars and neutron star crustquakes to even more exotic proposals. Among these is the suggestion that FRBs might be the signature of white holes, a sudden release of energy expelled from a region of space-time without warning, producing a coherent and high-intensity radio signal. It is, at the very least, consistent with the sort of impulsive outflow a white hole might create. Ultra-high energy cosmic rays add yet another layer to the mystery. These are particles, often protons or atomic nuclei, that strike Earth's atmosphere with energies millions of times higher than anything produced by our most powerful particle accelerators. Their origins are difficult to trace, in part because their paths are bent by magnetic fields as they travel through space. Some theories suggest that decaying dark matter or the collapse of topological defects in the early universe could be responsible. But others have proposed that these particles might be ejected from white holes, especially those that could exist briefly during rare quantum gravitational events. If a white hole released a burst of matter and radiation in an isolated region of space, it could accelerate particles to extremely high energies in the process. Despite the imaginative appeal of these ideas, identifying a white hole observationally remains an enormous challenge. The difficulty lies in distinguishing a white hole from other astrophysical explosions that share similar characteristics. GRBs, FRBs, and cosmic rays are already explained, at least in part, by conventional models involving neutron stars, black holes, and exotic magnetic phenomena. Any candidate event must be shown to exhibit behaviors that cannot be attributed to these known processes. So far, no such definitive anomaly has been observed, and even if one were, linking it to a white hole would require more than just energetic outbursts. It would require an understanding of the causal structure of the event. Evidence that no precursor existed, no matter was gathered beforehand, no accretion disk had formed, and no gravitational collapse took place. This is where observational astronomy meets its limits. Our instruments, though incredibly sophisticated, are often capturing only brief snapshots of events that occurred millions or even billions of years ago. By the time a signal reaches us, it is just a ghost, a remnant of a process long finished. Telescopes like the Fermi Gamma Ray Space Telescope, the CHIME Radio Telescope, and the Pierre Auger Observatory are helping to build a more complete picture, but the data remains frustratingly incomplete. The transient nature of these phenomena makes them difficult to study in real time. Follow-up observations are often too late to capture the event's immediate environment, and in many cases, the source fades completely. What would be needed to identify a white hole beyond doubt? One possibility is the detection of a one-time explosive event in a truly empty region of space, with no prior signs of stellar activity. The absence of any progenitor would be a strong, though not definitive clue. Another would be the spectral signature of the ejected material. If a burst exhibited energy distributions inconsistent with supernova, neutron star mergers, or magnetars, it might suggest an alternative origin. Even more compelling would be the identification of unusual gravitational lensing or space-time curvature associated with the event, something that hints at an exotic geometry inconsistent with a conventional collapse. Theoretical work can aid in this search by developing more precise models of white hole emissions. If physicists can predict the exact frequency spectrum, polarization, or spatial structure of a white hole outburst, observers can begin to compare those predictions with real events. Computer simulations of white hole formation and ejection could also help to identify telltale features. These simulations, however, are complicated by the instability of white hole solutions, as discussed in earlier chapters. Most white holes modeled so far collapse quickly upon perturbation, limiting their potential lifespan and observational signature. Nonetheless, even a momentary burst might be enough if the instruments are ready and the signal is unmistakable. There is also the question of whether white holes, if they exist, are rare or common. If they are the end products of black hole evaporation, as some quantum gravity models suggest, then they may be exceedingly rare and nearly impossible to detect with current technology. The final stage of Hawking radiation is expected to be brief and dominated by quantum processes that are not yet fully understood. If, on the other hand, white holes are primordial, formed during the chaotic birth of the universe, they may no longer be active, or they may exist only as fossil relics. And if they arise from quantum fluctuations, they may appear and vanish on timescales far shorter than we can observe, making their detection a matter of statistical chance. Some researchers have speculated that what we call a white hole might not be a single, monolithic structure, but a class of phenomena defined by shared behaviors rather than exact identities. In this view, white holes might manifest in many forms, some lasting milliseconds, others longer. Some might eject only photons. Others might release a mix of radiation and particles. Some might leave behind traces, others nothing at all. The term white hole could thus be less about a precise object and more about a behavior, a sudden non-causal ejection of mass energy into space-time. Even so, the burden of proof remains high. Science demands not just possibilities, but evidence. It requires reproducibility, consistency, and explanatory power. Until we observe a phenomenon that cannot be explained by any other means, white holes will remain theoretical. They may be hidden in plain sight, but we will need to learn how to truly see them. And yet, the search is valuable in itself. In looking for white holes, we refine our models, sharpen our instruments, and deepen our understanding of the universe's most violent and mysterious phenomena. Each unexplained signal is an invitation to look closer. Each gap in our data is a space where new physics might unfold. Whether white holes are real or not, they push us to ask better questions and to consider that nature may still have surprises left in store. Perhaps somewhere in the silent dark, a white hole is blooming. Just once, just briefly, flinging out the contents of a vanished world. And perhaps across time and space, a radio dish turns toward it at the perfect moment. A burst of light, a fleeting anomaly, a whisper from the edge of what can be known. Chapter 6. Wormholes and Bridges. Are white holes the exit? The idea of a bridge between distant regions of the universe, or even between different universes altogether, has captivated physicists and storytellers alike for nearly a century. This hypothetical construct, known as a wormhole, is often depicted as a tunnel through space-time, a shortcut that links two otherwise unconnected locations. It is a concept born not from imagination alone, but from the mathematics of general relativity. And at the heart of its earliest formulation lies a surprising and often misunderstood structure: the white hole. To understand the connection between white holes and wormholes, we must return to one of the most foundational exact solutions in general relativity, the Schwarzschild metric. This solution, discovered in 1916, describes the space-time geometry surrounding a spherical, non-rotating mass. While originally intended to model the space around stars and planets, it soon revealed stranger implications. As the understanding of event horizons and singularities matured, physicists began to extend the Schwarzschild solution beyond its initial domain, seeking a more complete picture of the space-time it described. This endeavor culminated in the development of the maximally extended Schwarzschild solution, formulated most elegantly using Kruskal-Sekaris coordinates. This extension revealed a surprising global structure. The spacetime of a non-rotating black hole was not a simple one-region geometry, but rather a manifold composed of multiple distinct regions. There was the exterior region, the one familiar to observers like us, and the interior black hole region past the event horizon. But on the opposite temporal side of the singularity was another region, mirror-like and time-reversed, a white hole. And beyond that, yet another asymptotically flat external region, appearing almost as a separate universe. This interconnected structure became known as an Einstein-Rosen bridge, named after Albert Einstein and Nathan Rosen, who explored this solution in 1935. In their formulation, the bridge appeared to be a kind of mathematical tunnel, a throat linking two separate regions of spacetime. The initial hope was that such bridges might eliminate the need for singularities, perhaps even modeling fundamental particles as smooth, non-singular geometric structures. But the bridge was not stable. In fact, it was non-traversable. Any attempt to cross from one region to the other would fail. The passage would collapse too quickly, pinching off before anything could make it through. In this geometry, the white hole and black hole form the two ends of the bridge. The black hole draws matter inward, leading to a singularity. The white hole ejects matter outward, emerging from its own singularity. Yet this is not a practical travel corridor. It exists only in the mathematical sense, as part of the complete Schwarzschild spacetime. The bridge is momentary and collapses faster than any signal or particle could traverse it. For all its intrigue, it remains a theoretical mirage, a structure that connects without allowing connection. Still, the idea persisted. The presence of a white hole at one end of the bridge suggests a tantalizing possibility. Could information or even matter fall into a black hole and emerge from a white hole elsewhere? Could white holes be the cosmic exit doors paired with black hole entrances? This question gains urgency in the context of the black hole information paradox, a puzzle that arises from the apparent destruction of information inside black holes. If quantum mechanics is to be believed, information cannot be lost. Yet black holes, with their event horizons and singularities, seem to offer precisely that fate for anything unfortunate enough to fall inside. Some theorists have proposed that white holes might offer a resolution to this paradox. Perhaps, instead of vanishing forever, the information swallowed by a black hole is eventually released through a white hole, whether in the same universe or another. This could occur not through a stable wormhole, but through a process in which the black hole evolves into a white hole over time, a scenario explored in certain approaches to quantum gravity, including loop quantum gravity. In these models, the singularity at the center of a black hole is replaced by a quantum bounce, and the geometry continues on the other side as a white hole. The transition is not a traversable wormhole in the classical sense, but a quantum-bridged evolution of space-time. This brings us to the deeper question of traversability. While Einstein-Rosen bridges are non-traversable, could other kinds of wormholes, perhaps stabilized by exotic forms of matter, allow passage from one region to another? Theoretically, the answer is yes. In 1988, physicists Kip Thorne and Michael Morris explored the possibility of traversable wormholes held open by negative energy. This kind of energy, though not found in ordinary matter, is not entirely forbidden by the laws of quantum field theory. Casimir effects and quantum fluctuations suggest that under certain circumstances, small amounts of negative energy density can exist. If sufficient negative energy could be arranged in the right configuration, it might counteract the natural tendency of the wormhole throat to collapse, keeping the passage open long enough for something or someone to cross. In these models, the wormhole could connect distant points in space-time, even allowing for shortcuts between galaxies or across vast cosmological scales. But the requirements are extreme. The amount of negative energy needed and the precision with which it must be configured are well beyond current or foreseeable technology. Moreover, stability remains a major problem. Wormholes, if they exist at all, are expected to be highly sensitive to perturbation. Any attempt to enter or send signals through them might cause them to pinch off or destabilize. Still, in these speculative frameworks, white holes continue to play a conceptual role. They act as endpoints, regions from which matter and information might emerge after having traveled through the hidden corridors of space-time. Even if traversable wormholes are physically unrealizable, the geometry that links white holes and black holes provides a useful mental model for understanding deep connections in space-time. It challenges our assumptions about locality, causality, and the linear flow of time. Recent developments in holography and quantum entanglement have even revived the idea in new forms. The ER=EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, suggests a profound relationship between Einstein-Rosen bridges and quantum entanglement. In this view, a wormhole connecting two black holes may be dual to a pair of entangled particles in quantum mechanics. The connection is not spatial in the classical sense, but rather a deep equivalence between geometry and quantum information. In some extensions of this idea, it is speculated that entanglement between a black hole and its Hawking radiation could give rise to a wormhole-like geometry through which information escapes, a kind of virtual white hole process, not visible to outside observers, but real in the quantum mechanical sense. Despite these theoretical insights, there remains no observational evidence for wormholes or for white holes. No signature of a space-time bridge has been detected in gravitational waves, gamma-ray emissions, or the cosmic microwave background. But the possibility remains open. If a white hole were to appear in the sky as a one-time burst with no progenitor, it might hint at a collapsed throat from a hidden wormhole. If the burst carried imprints of quantum information, non-thermal correlations in its radiation, it might suggest a history on the other side. These are bold speculations, but they form part of the frontier of theoretical astrophysics. Wormholes and white holes both sit at the edge of what general relativity allows and what quantum theory complicates. Their mathematical elegance is not questioned, but their physical realization is deeply uncertain. The idea that one could fall into a black hole and emerge from a white hole on the other side, perhaps in another universe or another time, remains a powerful image. Yet everything we know about space-time dynamics, causal structure, and energy conditions suggests that such a journey is not currently within the realm of the possible. And still, the image persists. Somewhere, perhaps far beyond our light cone, space-time might fold in on itself, twist, and emerge anew. Perhaps a signal, a memory, a particle of matter, swallowed by darkness, finds its way to light, reborn through a hidden tunnel. In that moment, the cosmos would not only stretch space but stretch meaning, reminding us that endings might hide beginnings, and that even in a universe ruled by entropy, the geometry of hope is never quite closed. Chapter 7. Replacing Singularities. Can white holes end collapse? In classical general relativity, singularities represent the breakdown of the theory itself. These are regions where space-time curvature becomes infinite, the laws of physics cease to be predictive, and quantities such as density and temperature are no longer finite. Singularities emerge in the center of black holes, as well as in some models of the early universe, like the classical Big Bang. Their presence is a mathematical signal that general relativity, powerful and accurate though it is, has limits. As one approaches the singularity, the theory stops being useful, and something deeper is needed. Physicists do not generally believe that singularities exist in a physical sense. Rather, they interpret these infinite quantities as indicators that the theory is being applied beyond its domain of validity. Much as Newtonian mechanics fails at relativistic speeds, general relativity is expected to fail under extreme conditions of curvature and energy density. These are precisely the conditions where quantum effects can no longer be ignored. A more complete theory of gravity, one that merges general relativity with quantum mechanics, is required to describe what really happens when matter is compressed to such extremes. The resolution of singularities is one of the central goals of quantum gravity. Various candidate theories, including loop quantum gravity, string theory, and asymptotically safe gravity, have been developed in part to address this issue. Interestingly, many of these approaches suggest that the singularity might not be the end of the story. Instead of collapsing into a point of infinite density, matter could undergo a kind of bounce, a transition from collapse to expansion. And in some scenarios, this rebounding matter emerges not as diffuse radiation, but as a white hole. This is where white holes enter the discussion in a new and profound way, not merely as the time-reversed twins of black holes, but as possible outcomes of quantum-corrected gravitational collapse. In this view, white holes are not eternal objects embedded in a static spacetime. Rather, they are the dynamic consequence of a quantum bounce, the process through which a collapsing black hole transitions into an expanding white hole without ever forming a true singularity. One of the most well-developed models exploring this idea comes from loop quantum gravity, a theory that attempts to quantize space-time itself by describing it as a network of discrete loops. In this framework, the geometry of space is not continuous, but made up of tiny, indivisible units, quanta of area and volume. As matter collapses under gravity, the density increases until it reaches a critical threshold near the Planck scale, where quantum effects dominate. At this point, a repulsive quantum pressure is hypothesized to counteract the classical pull of gravity, halting the collapse before a singularity forms. The result is what has been called a Planck star, a hypothetical core that forms inside a black hole, compressed to near Planckian density, but still governed by quantum gravity rather than classical divergence. Over time, the Planck star could re-expand, releasing its energy and mass back into spacetime in a highly energetic burst. To an external observer, this re-expansion might appear to come from nowhere, resembling the behavior of a white hole. Importantly, this process could preserve the information that fell into the black hole, offering a possible resolution to the information paradox. What makes this idea especially compelling is that it avoids violations of known physical laws. The bounce does not require exotic matter, violations of energy conditions, or modifications of relativity on large scales. Instead, it relies on a quantum correction to the behavior of spacetime under extreme curvature. The bounce is not visible to classical observers because the timescales involved can be stretched by relativistic effects. From the outside, the black hole might persist for billions of years before transforming into a white hole. From the inside, however, the bounce could occur almost instantly, thanks to the effects of time dilation near the event horizon. This temporal asymmetry opens up a subtle but fascinating possibility. White holes might be the end state of black holes, not their opposite. Rather than being objects that exist from the beginning of time, white holes could form at the very end of a black hole's life, after Hawking radiation has evaporated most of its mass, and quantum gravity effects become dominant. The final act of the black hole would not be disappearance, but reversal, a quantum burst in which the remaining information and energy are ejected in a brief flash, consistent with thermodynamic laws. The implications of such a process are profound. If black holes do not lead to singularities, but instead to white hole rebirths, then the ultimate fate of collapsing matter is not loss, but transformation. Information is not destroyed, but reprocessed. The geometry of space-time is not torn apart, but reshaped. In this view, The black hole is not a final grave, but a transitional state, part of a larger cycle in which collapse leads not to silence, but to renewal. Other theoretical frameworks explore similar ideas from different angles. Some extensions of general relativity, incorporating higher-order curvature terms or torsion, also yield bounce-like solutions. In these models, the singularity is replaced by a finite minimum radius beyond which further compression is not possible. The result is a structure that contracts, reaches a turning point, and then re-expands. Depending on the surrounding conditions, this re-expansion might occur into the same universe or into another region of space-time. If the bounce is asymmetric in time, it could produce an outward expanding object, a white hole, visible to external observers as a sudden burst of energy. Not all of these models are created equal. Some violate key physical principles or rely on untested assumptions. Others require modifications to energy conditions or introduce hypothetical fields that have not been observed. Still, the trend is consistent. A growing number of quantum gravity theories suggest that singularities may not be the endpoints we once thought. Instead, they may be replaced by new structures that respect both the symmetry of general relativity and the probabilistic laws of quantum theory. It is important to note that these ideas, while elegant, remain speculative. There is no direct observational evidence for Planck stars, quantum bounces, or white holes emerging from black holes. Yet these models offer testable predictions. For example, the final burst from a black hole-white hole transition might produce a distinct spectral signature or leave an imprint in gravitational waves. If these events occur within the observable universe, future instruments could detect their telltale signs. Advanced gamma-ray observatories, gravitational wave detectors, and neutrino telescopes may all play a role in this search. Even now, some researchers are reanalyzing data from past transient events, looking for anomalies that might hint at such a process. Could some unexplained high-energy outbursts be the final act of ancient black holes transforming into white holes? Could some seemingly causeless flashes in deep space be the echoes of bounces long hidden behind event horizons? These are open questions, but they are now taken more seriously than ever before. Beyond the scientific implications, the notion that white holes could mark the end of collapse offers a shift in how we understand the life cycle of matter and space-time. It replaces finality with transformation, erasure with continuity. Instead of confronting an abyss of infinities, physics may be converging on a vision of the cosmos that is complete, where every process has a continuation, and nothing, no information, no geometry, is truly lost. This perspective brings together the symmetry of Einstein's equations with the probabilistic nature of quantum mechanics. It offers a coherent, if incomplete, picture in which black holes do not violate the unitarity of quantum theory, and space-time does not self-destruct under pressure. In that picture, white holes are not merely theoretical inverses of black holes. They are part of a deeper truth. That space-time, when pushed to its limits, responds not by breaking, but by adapting. Perhaps then, the end of gravitational collapse is not silence, but a second beginning. Perhaps the last whisper of a black hole is not its evaporation, but its reversal. And perhaps, in some distant region of the universe, a white hole has already begun to blossom. Not as a relic of the past, but as a continuation of something once thought lost. In such a universe, even the most extreme processes lead not to nothingness, but to change. The cosmos does not tear itself apart. It folds, compresses, and returns. And in the heart of collapse, there may still be light. Chapter 8: The Big Bang as a White Hole. The origin of our universe is a question that has captured scientific inquiry and philosophical curiosity in equal measure. The standard cosmological model tells us that everything we see, the galaxies, stars, planets, and even the fabric of space and time itself, emerged from an extremely hot, dense, and rapidly expanding state known as the Big Bang. While this model is supported by a wealth of observational evidence, including the cosmic microwave background and the expansion of space, it still leaves one question unresolved. What, if anything, came before? At the heart of this question lies the Big Bang singularity. In classical general relativity, the backward extrapolation of the universe's expansion leads to a point where densities and temperatures become infinite. This is not a physical object or place, but a boundary in time, a mathematical singularity where known physics breaks down. The same kind of singularity appears inside black holes, raising a tantalizing possibility. If black hole singularities and Big Bang singularities share a common mathematical structure, might they also share a common physical explanation? Could the Big Bang itself be the birth cry of a white hole? This idea, while speculative, is rooted in serious theoretical work. The similarities between the behavior of a white hole and the conditions of the early universe are not superficial. Both involve rapid, high-energy expansion from a seemingly causeless boundary. Both feature a one-way flow of matter and energy from a region that cannot be probed or entered. Both are characterized by extreme curvature, relativistic outflows, and an absence of internal observers. In effect, the observable universe resembles what a white hole would look like from the inside. One line of thought comes from the idea of time reversal symmetry. Just as a black hole appears to collapse matter into an unreachable singularity, a white hole appears to emit matter outward from one. If time is fundamentally symmetric, then it is not unreasonable to imagine that what we call the Big Bang might be the time-reversed image of a gravitational collapse. Instead of being a beginning, the Big Bang could be a bounce, a transitional phase from one universe to another. In this framework, our universe could be the interior of a white hole that formed from the collapse of matter in a different region of space-time. This concept has been explored under the umbrella of black hole cosmology, an idea suggesting that each black hole might give rise to a new universe on the other side of its singularity. In such models, when a massive star collapses into a black hole, the internal geometry does not end in destruction, but continues beyond the singularity. The extension could appear from the inside as a new expanding universe, a new Big Bang. The exterior observers see a black hole. The interior observers experience an inflating cosmos. From this perspective, the formation of a black hole in one universe becomes the creation event for another, forming a cosmological tree in which universes beget universes. These ideas go beyond metaphor. In general relativity, the equations governing the interior of a black hole can be extended mathematically into regions that resemble expanding universes. The Einstein field equations do not forbid such a continuation. They allow for geometries where collapse is followed by expansion. However, the singularity remains a problem. Classical gravity predicts that all matter collapses to a point of infinite density, and from there, no further evolution is defined. This is where quantum gravity comes into play. In particular, loop quantum cosmology, a simplified model derived from loop quantum gravity, provides a framework in which the Big Bang singularity is replaced by a bounce. Instead of space and time terminating at a point of infinite density, quantum corrections generate a repulsive force at small scales. This repulsion counteracts gravity and causes the universe to rebound. The pre-bounce phase could be a contracting universe, perhaps similar to our own in reverse. The expansion we see today would then be the second act in a cosmic cycle, one born not from nothing, but from the wreckage of a previous cosmic stage. This quantum bounce mirrors, in many ways, the idea of a white hole. The compression of matter in the pre-bounce phase mimics the gravitational collapse that leads to a black hole. The bounce itself replaces the singularity, and the subsequent expansion resembles the emission from a white hole. Importantly, the The process conserves information and energy, aligning with the fundamental principles of quantum theory. One version of this idea is the Planck star model, where the interior of a black hole becomes so dense that it triggers a quantum gravitational repulsion, halting the collapse. After a certain time, the compressed matter re-expands, forming a new universe. From the perspective of the new universe, this event appears as a Big Bang. From the perspective of the parent universe, the black hole remains an object with an event horizon. Time dilation ensures that the bounce takes an unimaginably long time from the outside, but nearly no time from the inside. Could our universe have emerged this way? It's a possibility that cannot be ruled out. If the conditions at the Big Bang correspond to the quantum bounce of a previous collapsing universe, then the observable universe may indeed be the interior of a white hole. Such a scenario does not require speculative physics beyond what is already considered in modern theoretical research. It simply reframes our understanding of the Big Bang not as an ultimate beginning, but as a transitional phase, an interface between contraction and expansion, between one universe and the next. Historically, this idea connects surprisingly well with early cosmological debates. Georges Lemaitre, one of the founders of Big Bang theory, referred to the origin of the universe as a cosmic egg that exploded at the moment of creation. This metaphor, though predating white hole concepts, evokes the same notion of contained energy suddenly emerging. In later decades, as black holes became a central topic in gravitational theory, the realization that singularities mark both ends of the time arrow, inside black holes and at the Big Bang, led researchers to question whether these singularities could be linked. There are several implications of this perspective. First, it offers a resolution to the problem of the initial low entropy of the universe. If our cosmos emerged from the interior of a black hole, the order of its initial conditions could be inherited from the structure of the previous universe. Second, it provides a natural mechanism for cosmic inflation. The extreme repulsive force required for the bounce could drive rapid expansion, aligning with observations of the early universe's uniformity and flatness. And third, it suggests that universes may be interconnected, not spatially but causally, through processes of collapse and rebirth. Observationally, testing this hypothesis is difficult. The universe's observable horizon is limited, and the conditions near the bounce are hidden behind the veil of the Planck era, when quantum gravitational effects dominate and classical space-time concepts break down. However, some signatures might survive. Certain patterns in the cosmic microwave background, anomalies in the distribution of large-scale structures, or the absence of predicted singularities in gravitational wave events could point toward a bounce scenario. Some researchers have proposed looking for subtle correlations in polarization modes of the cosmic microwave background that could reveal traces of a previous contracting phase. Others are exploring whether the information emitted during hypothetical white hole bounces could leave high-energy imprints, perhaps even seeding the initial density fluctuations required for galaxy formation. Although no such signatures have been definitively identified, ongoing missions like the James Webb Space Telescope and future projects such as the Cosmic Origins Explorer may offer the resolution and sensitivity needed to probe deeper into the infinite universe than ever before. From a geometric standpoint, a white hole origin would have implications for the global topology of spacetime. The causal structure of the universe would include regions inaccessible to any observer, areas beyond the bounce from a preceding contraction. This changes the way we think about causality itself. Instead of an absolute beginning, we are dealing with a boundary condition, one that is local in time, but potentially connected to a broader, perhaps eternal structure. The event horizon of a black hole becomes, in this view, a kind of bridge, not to another place, but to another temporal domain. Philosophically, the idea that the universe could emerge from a white hole is provocative. It suggests that creation is not ex nihilo, not from nothing, but from a rearrangement of pre-existing space-time structure. In this model, beginnings are illusions created by horizons, limits beyond which we cannot see, but not necessarily beyond which nothing exists. The Big Bang becomes a portal, not a point. And we, living on the inside of this vast expanding bubble, may be part of a larger cycle, an echo of collapse transformed into expansion. While this vision is compelling, it remains speculative. The theoretical groundwork is still developing, and the observational evidence is far from conclusive. Yet the fact that general relativity and quantum theory can be combined to yield such a coherent picture is a remarkable achievement. It shows that our best physical theories, even when incomplete, are capable of inspiring new ways to understand the universe's deepest mysteries. The Big Bang as a white hole is not a settled fact. It is a proposal, a lens through which to view the cosmos. But it is a proposal that aligns with fundamental symmetries, with the desire to remove singularities from our equations, and with the hope that no event, no collapse, no death is truly final. If true, it means we are living inside a rebirth. Our universe would not be the first nor the last, but one thread in a vast and possibly infinite fabric. The light we see in the sky would be the echo of a bounce from another realm, and time, as we experience it, would be only a chapter in a story that never really begins and never truly ends. Chapter 9. Why we've never seen one and why that might change. White holes, though permitted by the mathematics of general relativity, remain entirely hypothetical. Unlike black holes, which have accumulated robust indirect and direct observational support over decades, white holes continue to exist only as theoretical possibilities. Their absence from astronomical data is not necessarily a disproof of their existence. Instead, it highlights the enormous difficulty in detecting an object so radically different from anything else we have ever observed. In this chapter, we explore why we've never seen a white hole, and why, despite those challenges, future technologies and theoretical progress may bring us closer to doing so. The most immediate reason for the absence of white hole observations is their expected instability. A white hole, by definition, does not allow anything to enter its event horizon. It is the time-reversed version of a black hole, a region from which matter and light emerge but into which nothing can fall. While this sounds intriguing, it creates a significant problem when it comes to the real universe. Any disturbance, even the tiniest influx of matter or radiation from the surrounding cosmos, would likely destroy the white hole structure. In theoretical analyses, white holes are incredibly sensitive to perturbations. They are not protected by the same kind of event horizon shielding that stabilizes black holes. Instead, a single photon arriving at just the wrong moment could be enough to collapse the entire white hole back into a black hole. This inherent fragility makes it extremely unlikely for white holes to exist for long in a chaotic, radiation-filled universe like ours. Adding to this challenge is the notion that if white holes do form, they may do so only under very rare conditions. Unlike black holes, which are known to form from the collapse of massive stars or from the mergers of dense stellar remnants, no known astrophysical process naturally leads to the creation of a white hole. Their hypothetical formation scenarios are more abstract, either as theoretical solutions to equations of general relativity, as end states in quantum bounce models, or as components of speculative cosmologies involving wormholes or multiverse branching. Each of these possibilities adds a layer of complexity and a filter of improbability, making the actual detection of a white hole an exceedingly elusive task. There's also the matter of their potential lifespan. If white holes do form, the theory suggests they may exist only momentarily. In models involving Planck scale physics, such as those based on loop quantum gravity, a white hole may be the brief endpoint of a quantum bounce, existing for an instant in cosmic time before dissipating or transitioning into a different state. If this is the case, even the most sensitive observational tools may not catch them in action. Not because they aren't there, but because they vanish before we can measure them. Yet despite these difficulties, the situation is not hopeless. We are living in a new era of observational astronomy, one marked by instruments that peer further, measure faster, and resolve finer details than ever before. The James Webb Space Telescope, JWST for instance, is already revolutionizing our understanding of the early universe. With its deep field capabilities, it may uncover unusual sources of high-energy radiation, compact ejecting objects, or short-lived bright bursts that defy current models. If a white hole ever manifested as a brief, intense event, such as a sudden expulsion of energy and matter, it might leave behind a signature detectable by telescopes sensitive to extreme ultraviolet or infrared light. While no such observations have been confirmed to date, astronomers are increasingly aware that they must keep an open mind about anomalous phenomena. In the realm of high-energy astrophysics, fast radio bursts, FRBs, and gamma-ray bursts, GRBs, have already puzzled scientists with their suddenness and intensity. Some speculative theories suggest that these brief flashes might be linked to white hole events. The idea is that, under specific conditions, a white hole's expulsion of material could appear as a very short but powerful pulse of energy, something like a gamma-ray burst, but with slightly different spectral or timing properties. While most FRBs and GRBs have likely explanations involving neutron star mergers, magnetars, or black hole activity, there remains a category of outliers that do not fit existing models cleanly. A white hole origin for these events is still highly conjectural, but it is precisely in the unexplained margins where discovery tends to happen. Gravitational wave astronomy may also provide new avenues for white hole detection. Since 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, has opened up a new spectrum through which we can perceive the cosmos, not by light, but by ripples in space-time itself. Gravitational waves are generated by the acceleration of massive objects, particularly during mergers or violent collapses. If a white hole were to rapidly expel mass in a non-symmetric fashion, or if it formed as a bounce from a black hole-like singularity, it could leave behind a gravitational wave signature distinct from those produced by known processes. The current generation of detectors may not be sensitive enough to resolve such an event, especially if it occurs at the Planck scale or over ultra-short durations. But future upgrades and next-generation detectors such as the Einstein telescope or LISA may expand our sensitivity window into these domains. Another promising development lies in computer simulations and theoretical modeling. As computational power increases and our understanding of quantum gravity improves, scientists can generate more refined predictions of what a white hole might look like, from the inside, from a distance, and during its formation or collapse. By simulating possible emission profiles, radiation spectra, and space-time perturbations, theorists can create templates that observational astronomers might use to compare with real data. If a telescope captures a signal that doesn't match known black hole or supernova models, a white hole simulation could offer an alternative explanation. In this way, theory and observation form a feedback loop, each guiding the refinement of the other. But what would it actually take to prove that a white hole exists? The challenge lies in distinguishing its signal unambiguously from other high-energy phenomena. A true white hole would need to exhibit several features: unidirectional emission of mass energy from a causally disconnected region, an absence of infalling matter, and perhaps even signs of negative time curvature in the local space-time geometry. These are not simple measurements. Most of them are not directly observable at all. Instead, they would need to be inferred from indirect observations. Subtle asymmetries in energy release, time reversal symmetry in simulations, or statistical anomalies across a population of cosmic events. It would also require a paradigm shift in how we interpret such phenomena. Much like how black holes were once dismissed as theoretical oddities before being accepted as real astrophysical objects, white holes will remain hidden until enough circumstantial evidence accumulates to force a new consensus. This shift may come not from a single observation, but from a pattern, an accumulation of unexplained events that together suggest a new class of object. In the end, proving the existence of a white hole may involve more than detection. It may require reinterpretation of existing data through the lens of new theory. Of course, even if we do find such a signal, profound questions remain. How did the white hole form? Is it the result of quantum gravity, a relic from another universe, or a feature of a deeper, unknown layer of physical law? If it exists now, how long will it last? What happens to the information and matter it expels? These questions tie back into the broader context of cosmology and fundamental physics. They remind us that a white hole is not merely a hypothetical object. It is a symbol of the boundaries of our understanding. It is also possible that white holes have already appeared in the universe, but so briefly and so far away that we have not been able to catch them. The observable universe is limited by the speed of light and the age of the cosmos. There may have been white holes in the very early universe, just after the Big Bang, or even before it in cyclic models, but their light may have been redshifted beyond detectability or diluted by cosmic expansion. Their gravitational waves may be too faint, too fast, or too buried in noise to extract with current tools. In this sense, white holes may exist not just beyond our instruments, but beyond our reach. And yet, we keep searching. With each improvement in telescope resolution, each upgrade in gravitational wave sensitivity, and each breakthrough in quantum gravity, the probability of finding evidence increases. If white holes do exist, then somewhere in the cosmos, there must be a trace, a fingerprint left in the fabric of space-time, waiting for us to decode it. The idea that we may one day detect something so fundamentally alien to our experience is both humbling and thrilling. If white holes exist, they may show us that not all processes in the universe are irreversible, that not all collapse ends in darkness. They would demonstrate that the universe not only conceals, but sometimes reveals, explosively, fleetingly, and mysteriously. And perhaps in some distant place or future time, a white hole will open its brief window into elsewhere, and the universe will whisper a story we've never heard before. Chapter 10. The White Hole Frontier, What We Still Don't Know. White holes, despite their elusive nature, continue to occupy a significant space in theoretical physics. They are not merely the exotic opposites of black holes, but rather windows into some of the deepest unsolved questions in our understanding of reality, questions about time, causality, information, and the fabric of space-time itself. As we reach the final frontier of this topic, we must contend with both the richness of mathematical possibility and the sobering humility of observational silence. The notion of a white hole challenges our most basic intuitions about the directionality of physical processes. In everyday life, time flows in one direction. A cup falls from a table and shatters. It does not spontaneously reassemble and leap back. Smoke rises and disperses. It does not concentrate and collapse into a matchstick. This irreversibility is a consequence of entropy, the statistical tendency for systems to move from ordered states to disordered ones. But the fundamental laws that govern particles, fields, and space-time do not inherently possess this asymmetry. The equations of general relativity, and even those of quantum field theory, are time-symmetric. They allow processes to occur forward or backward in time with equal legitimacy. White holes emerge from this symmetry. If the equations that allow a black hole to collapse and trap information inescapably also work in reverse, then it is not unreasonable to imagine a scenario where matter and information are expelled from a singularity instead of drawn into it. Mathematically, such a solution is valid. The so-called maximally extended Schwarzschild solution includes both a black hole region and a white hole region, separated by an event horizon. From this perspective, white holes are not inventions. They are natural, if peculiar, residents of the general relativistic landscape. And yet, physics is not just mathematics. A solution to Einstein's equations does not guarantee physical reality. There are countless mathematically consistent spacetimes that describe situations unlikely to exist in the real universe. Some with closed time loops, others with disconnected regions, still more with exotic topologies. What distinguishes the physically meaningful from the merely mathematical is not just logic, but also evidence. And when it comes to white holes, that evidence remains frustratingly absent. Still, white holes keep returning to the forefront of theoretical discussion, and not merely because of their aesthetic appeal. They appear, often unexpectedly, in serious attempts to resolve paradoxes in black hole physics, in quantum gravity, and in cosmology. Their persistence is not a matter of philosophical indulgence, but of scientific necessity. Consider the black hole information paradox. According to classical general relativity, information that falls into a black hole is irretrievably lost once it crosses the event horizon. But this conclusion contradicts the principles of quantum mechanics, which dictate that information cannot be destroyed. This tension has led to decades of debate and has spurred numerous proposals, including holography, black hole complementarity, and the firewall hypothesis. In several of these models, white hole-like structures appear as mechanisms through which information might be recovered, either via slow evaporation or through explosive ejection. In certain quantum gravity frameworks, especially those grounded in loop quantum gravity, white holes emerge not as exotic add-ons, but as inevitable consequences of the theory's internal consistency. When spacetime is quantized, the singularities of general relativity dissolve into finite, calculable structures. In these models, gravitational collapse halts at a minimal volume and then rebounds. What appears to be a black hole from the outside could transition into a white hole on the inside, releasing matter and information back into spacetime after an immense delay due to relativistic time dilation. Such ideas are not idle speculation. They are active research directions, complete with mathematical formalisms and evolving predictions. White holes also play roles in broader cosmological thinking. Some researchers have suggested that our universe itself might be the interior of a white hole that formed in a larger parent universe. In this view, white holes are not isolated anomalies, but the seeds of entire cosmic domains. They function as bridges between regions of space-time that otherwise appear causally disconnected. Whether through bounce cosmologies or black hole cosmogenesis, white holes offer potential explanations for the initial low entropy of the universe, the arrow of time, and even the conditions for inflation. Despite these advances, many fundamental questions remain unresolved. What stabilizes a white hole against collapse? Why haven't we seen any, even in indirect form? Can a white hole form spontaneously, or must it always be preceded by a black hole phase? Do they persist indefinitely, or are they transient, fleeting phenomena? These questions push us toward the limits of our current understanding. Much of the ambiguity stems from the fact that we still lack a fully developed theory of quantum gravity. General relativity treats spacetime as a smooth, continuous fabric, while quantum mechanics describes the world in discrete, probabilistic terms. Reconciling these two pictures remains one of the grand challenges of modern physics. White holes sit at the heart of this tension. They require a coherent account of singularities, of information conservation, of entropy across horizons, all issues that cannot be resolved within classical frameworks alone. In this sense, white holes are more than theoretical curiosities. They are signposts pointing toward the future of physics. Any breakthrough in our understanding of quantum gravity is likely to clarify their status. If loop quantum gravity continues to develop, we may find calculable conditions under which white holes form, evolve, and potentially reveal themselves. If string theory gains further traction, it may provide a holographic dual for white hole geometries, offering insight into their thermodynamics and quantum structure. And if entirely new approaches emerge, they may shed light on why time seems to have a preferred direction, or whether that preference is merely a feature of our perspective within a broader, bidirectional reality. Technological advancements will also play a critical role. Future telescopes may capture high-resolution images of distant, high-energy events that defy current categorization. New generations of gravitational wave detectors may uncover patterns inconsistent with black hole mergers or neutron star collisions. Deep space probes and fast radio telescopes may register bursts of radiation that match predictions for brief white hole outbursts. And ever-improving computational models will help us filter the data, seeking not just what is known, but what lies in the gaps between the known. Still, we must acknowledge the possibility that white holes, though theoretically sound, may not exist in our universe. The physical conditions required for their formation may never arise. They may be unstable by necessity, dissolving before they can ever manifest. Or they may lie beyond the horizon of observability, woven into a structure of reality that we cannot access from our present vantage point. If so, they remain valuable not for what they reveal directly, but for what they teach us about the limits of physical law and the importance of consistency in our theoretical frameworks. There is also the lingering question of interpretation. Even if an observation were made, a burst of unexplained radiation, a non-standard gravitational signal, a statistical anomaly in cosmic background data, would we recognize it as evidence of a white hole? Or would we assign it to some other process, more familiar, more easily reconciled with our current models? This challenge is not merely technical, it is philosophical. Our readiness to accept a new phenomenon depends not only on data, but on the theoretical scaffolding we build to understand it. And perhaps this is the most enduring role of white holes in science. They force us to confront the boundary between what we can calculate and what we can observe, between what we believe and what we can test. They remind us that physics is not a finished story, but an evolving conversation, shaped by new ideas, new tools, and a willingness to challenge the assumptions we've inherited. In a sense, white holes are the mirror of our epistemology. They are what we see when we follow our theories to their logical extremes. They may not be real in the way stars or galaxies are real, but they are real in the way that thought experiments are real, probes into the architecture of possibility. Whether or not they exist in the sky, they certainly exist in the fabric of our scientific imagination. And so we continue to wonder, could the universe contain regions where time flows backward, where entropy decreases, where information escapes instead of falling in? Could there be places, perhaps far beyond our cosmic horizon, where collapse ends not in silence, but in light? If white holes exist, they are more than just phenomena. They are messages, emerging not from stars or particles, but from the structure of reality itself. Perhaps the silence of the cosmos on this matter is not final. Perhaps it is only the pause before a new kind of discovery. And in that silence, in the space between what is known and what is dreamed, we might one day hear the first whisper of something breaking free, not into collapse, but into revelation. And there we are, friend, on on the edge of what we know and what we still dream might be. If you're still awake and curious, there's another video waiting for you. But if your eyes are starting to close, then sweet dreams out there among the stars.